Section 9.3, Confidence and Prediction Intervals, Video 4. So let's do an example. Consider the following outputs for bill versus tip. We're going to calculate the 95%, not prediction interval yet. We'll do that second. Confidence interval for a bill value of $30. Now, you may have noticed that I didn't put a star on the bill. I was looking in the textbook, and most of the time, the only time they put a star on a variable is when it's specifically the letter X. Technically speaking, you can put a star on any variable that we are using as the specific value of the predictor. In this case, the specific value of the bill being $30. But to be consistent with the book, I will refrain from putting a star on anything but an X. But just remember, X star means the specific value of the predictor. In this case, X star would be 30. All right, so let's take a look at the three types of computer outputs that we can be given. And on your next test, I will give you all these outputs, and you need to understand what information they contain. One set of output are summary statistics, which simply list your variables, how many of each one you have, the means of each variable, and the standard deviation of each variable. The regression output is the same as we saw before when we reviewed regression in Chapter 2. We have a column listing the predictors, the first one being the intercept, the second one being the explanatory variable, which in this case is the bill. They're coefficients that we can use to build the linear regression equation. There's standard errors in case we're doing any estimating or testing of either of these. We only did the estimating and testing for the explanatory variable, not for the intercept. The t-value if we were testing, and the p-value if we were testing. For the ANOVA output, we still have the same three sources of errors as before, sources of variability from the model, from the errors that the model doesn't account for, and the total variability, their respective degrees of freedoms, the sum of squares for each one. We never actually did those formulas. We'll let the computer do the work for us. The MS's, and just remember that in any ANOVA table, the MS is always the SS divided by the degrees of freedom, which is why these two match, because the degrees of freedom is 1. The F statistic, which is the ratio of the MS's, so the first one, MS model divided by MS error, and then the p-value associated with that test statistic. If we were testing, is the model effective? There's a lot of questions I could ask you, but let's go to this confidence interval. The first move is to find t, and that's the same as it's always been. However, we do need to use the formula for degrees of freedom, which is n minus 2. Do you know what n equals in this setup? It's important that you know where to find it. There's actually a couple of places you can find it. In the ANOVA for regression table, the total degrees of freedom is equal to n minus 1. So if n minus 1 is 156, then n is 157. But in the summary statistics, it tells you what the n is. The reason it's listed twice, there were 157 bills, but there were also 157 tips. So there were 157 ordered pairs. So if the n is 157, then the degrees of freedom here is 155, which not by coincidence is the same as here because the formula there was n minus 2. So if you were to sketch a bell curve, drop 95% in the middle, that leaves 2.5% on either end, get out the t-chart. The degrees of freedom is so high, we would go to the infinity row, and so our t is going to be 1.960. Technically, plus or minus 1.960, but we only need the positive because we did the plus minus at the very end. All right, here's where things slow down. In order to calculate the standard error, first we need to calculate the standard error of deviations, the square root of MSE. So this is where the ANOVA table comes into play. MSE, mean sum of squares of errors, is 0.9595. So 0.9595 square rooted. Let's take that to 4 decimal places as soon as I can find a calculator. Here's a baby calculator, but it will get the job done. 0.9595 square rooted is 0.9795. So approximately 0.9795. It's not a surprise, it's pretty close to that. This is close to 1, and the square root of 1 is 1. So they're reasonably close. Then we can set up the formula for the standard error. I'm not going to rewrite the formula, but I'll cite the values as I set it up. The first value is the standard deviation of errors, so it's the value I just found, 0.9795, times a tall, long square root. The first part of the square root is 1 over n, and the n was 157. So 1 over 157. Plus a bigger fraction. On the top of the bigger fraction is a squared subtraction problem. On the left of it is the x star, the specific value for bill that we're looking at, which was $30. On the right side of the subtraction was x bar, the mean of all the bill values that were observed. That comes from the summary statistics. The mean of the bill values was $22.73. In the denominator, we have two things to multiply. One of them is n minus 1. So I'm going to go ahead and write 157 minus 1 just to emphasize the structure of the formula, but in practice, I would have just written 156 there. Times the square of the standard deviation of all the x's. That's in the summary statistics. The standard deviation of all the x's, oh, I'm sorry, by x I mean explanatory variable, which is bill. The standard deviation of all the bills was 12.16. So 12.16 squared. Now, this is a mess to put in a calculator. It can be done if you're very careful in one move, and if you have a decent calculator. I'm going to check my computer bag to see if I have a decent calculator in there. I should. Let's see. I do. Hooray. Okay. So I'm going to put all this in here in one fell swoop. I recommend trying to put it all in at once as opposed to doing multiple calculations and writing down the next step. The more you do that, the more you're rounding off and the more error there will be in your actual value. So 0.9795 times square root of 1 over 157 plus the quantity 30 minus 22.73 squared divided by the quantity 156 times 12.16 squared. I think I need to close off all my parentheses. And I got a syntax error. Well, that's discouraging. Oh, I see why. I did not press the correct symbol for square root. Where is it? I need new glasses. All right, let me make sure everything's set up correctly. I may have an extra open parentheses. I'm going to put it in one more time. I'm going to write down the answer that I got. But because I had to go back and edit something to fix a syntax error, I would feel remiss if I didn't go back and actually reevaluate this. I got 0.0912, but I'm going to try it one more time. This time I'm going to do something a little bit different. I'm going to start by figuring out this big fraction, add this fraction to it, square root it, and then multiply. But I'm not going to write down anything until the end. So let's start with this. Parentheses 30 minus 22.73, close parentheses squared equals, divided by, open parentheses, because I've got a giant denominator, 156 times 12.16 squared, close that parentheses, equals. Now I'm going to add 1 divided by 157 equals. Now I'm going to square root that, press equals, and now I'm going to multiply it times 0.9795, and I got the exact same answer I got before, so I guess I corrected my error the first time. Again, this is where most people are going to make their mistakes if they're not careful. You know, I give partial credit based on how many mistakes you make during a problem. So if this comes out incorrect, don't worry. As long as you do the correct thing you're supposed to do, you'll get credit from that point forward. You'll just lose points on this step. All right, third step is to find the margin of error, which is the product of the first two answers. So the t was 1.960. The standard error was 0.0912. So if we multiply that and round it to 4 decimal places, Might help if I press the decimal, times 0.0912. So I get a standard error of 0.1788. I can round, I promise I can. And so now we're ready to make our interval. But remember, our interval is centered around y hat. So first we have to calculate the y hat, which is, excuse me, in this context, y hat is tip hat. So the predicted tip is our equation, which is not on the board, with $30 inserted into it. So where's the equation? We have to dig it out of the regression. Remember, these are the coefficients for the regression. This is your intercept, this is your slope. So negative 0.292 plus 0.182 times the bill amount, which was $30. So if we put that in, we will get exactly 5.168. So our interval is going to be 5.168 plus or minus the margin of error, 0.1788. So if we do the subtraction problem, we get 4.9892, and if we do the addition problem, we get 5.3468. But let's think about it. We're trying to estimate the mean tip value. That's a dollar amount, so it makes sense to round these to 2 decimal places. I could have rounded earlier, but rounding earlier gives less exact answers at the end. I would wait to round it to 2 decimal. Wait to round it to 2 decimal places until the end. So 4.99 and 5.35, which I believe was the exact same confidence interval that we had previously. In the next video, we'll calculate the prediction interval. But remember, the only difference we have to make is here. We have to stick a 1 plus in there. So that will change the standard error, which will change the margin of error. It won't change this tip hat value, but it will change the final interval.